Okay, this is 5.7, scatter plots and lines of fit. This is really, if you're doing the Chapter 5 project, this section is pretty much the Chapter 5 project. Okay, first thing is correlation. Trying to, when you plot points, when you do a scatter plot, which is plotting points, you want to see if there's a relationship between the variables, the x and the y, if we're using x and y. And so if you plot your points and you notice that as the x gets bigger, so as you go in the x direction here, you notice that the y's also get bigger, then we're going to say that that has a positive slope, and we're going to say overall that it has a positive correlation. Okay? So x gets bigger and the y gets bigger at the same time. Like positive correlation. Definitely a relationship between the variables. Next thing that can happen is when you plot your points, you might notice that as the x gets bigger, the y actually gets smaller. So you can see that the x's are getting bigger to the right here, and then the y values are actually getting smaller. That gives us a negative slope, and we call that a negative correlation. So pretty simple. Sometimes when you plot things, they're kind of ridiculous. They don't have any relationship. Some people think that the size of their big toe has something to do with their IQ or some weird things that don't really have a relationship. So when you plot them, when you plot your data, it's just all over the place, and it doesn't show a clear relationship. So if that's the case, we're just going to say that it has no correlation, none that we can clearly see. Okay, so there's lots of interesting things. There's an infinite number of examples of things that have a relationship numerically, with the data. So this is a weightlifting one. You'll notice that when you lift more weight, notice the weight keeps going up. When you lift more weight, you aren't able to do as many repetitions. You know that. When you have light weight, you can do a lot of repetitions. Okay. I think when you're building, some lean muscle mass, you do a lot of repetitions. When you're building bulk, it seems like you do less repetitions, but you use more weight. So we can clearly see there's a negative correlation there with the dots. Okay. Another one, you know that as you spend more time exercising, you're going to burn more calories. So we clearly see dots are going up as the minutes are going up. Average jogging speed, that not necessarily for everybody, but on average, when people jog for longer, they may start decreasing their speed. I know that I would if I was jogging for 15 minutes, 20 minutes, 25 minutes, my speed would definitely, on average, start decreasing for me pretty rapidly. Okay, now here's kind of a full example that I want to do. So I think it's really interesting that people are living longer as the years go on. So what this is real data. I think it's for men. But this is the year they're born. So if a man was born in 1920, he was expected to live 54.1 years on average, assuming he didn't get hit by a car, have some other crazy thing happen. But on average, that's how long he was expected to live. In 1930, a man was expected to live to be 59.7 on average. So as it goes, every 10 years or so, besides this 5-year span, you notice it keeps going up. So clearly, when you plot these points, we want to see if there's a relationship. Well, there is. You notice that as the years go on here, that definitely people are living longer. And so not only do you want to see if there's a relationship, which we can tell is a positive correlation, but we might want to actually use that to predict things. So what we would do is we would plot the points and we'd say, okay, now we need a line that really does a nice job of fitting the data. That's where we come up with this line of best fit. So we come up with a line that we think does a nice job of modeling the data. So we draw a line, and we're going to disagree a little bit, potentially, on our line of best fit. But let's say I come up with a line that I think does a decent job of going through the points. So I'm going to try to use, doesn't have to go through the points, actually. It just kind of does a nice job of modeling. Maybe it even goes through just sort of the middle of the points. Okay. So let me see if I can draw a decent one. Like maybe this would be an example of a line of fit for this data. Okay, so there we go. After you draw your line of best fit, then we'd really like to write an equation to go with that. So then we go back to our skills from 5-4, 5-5, etc., where if we had 2 points, we definitely could write the equation of the line. This is one of the big reasons why you'd ever want to write an equation of a line. Okay? So choose 2 points that are actually on that line. It's going to be probably in our best interest if we pick a couple of points that are not only on the line, but they're actually part of the data set that we had, that we were given. So I'm going to choose these 2 points because I've kind of done some calculations. So 1930, 59.7, and then I'm going to pick another point that I think is on the line, 1970 and 70.8. So 2 points, a year, and then the number of years that they would live. Okay, so we just calculate the slope. So we say m equals, and if you're the type, that really label your points, then you would label this. You would say x sub 1, y sub 1, x sub 2, y sub 2. It's kind of a nice idea to do that. So then we subtract. We do 70.8 minus 59.7. And then now we subtract the x's on the bottom. So we have 1970 minus 1930. Subtract those. On the top, we should get 11.1. And then on the bottom, we should get 40. We can go ahead and pull our calculator out when we're working with real data like this. It's a good idea to use a calculator. So 11.1 divided by 40, we get 0.2775, and that's our slope. So remember what we do. When you have the slope, all you need is a point so that you can continue to, write the equation of the line. So what we would do is we would choose a point. So let's choose maybe this point here. And there are a couple ways to do it. You can use point slope form, or you can start with y equals mx plus b. I'm going to go ahead and just start off with y equals mx plus b. And actually, I'm going to use a new page for this. So there's my slope. I'm going to rewrite it on the next slide. Point. So m equals 0.2775. And the point I'm using is 1930, 59.7. Alright, so I'm going to plug 59.7 in here for the y. And the m is what we calculated, 0.2775. The x is right there. Just label that again. The x is 1930. And we don't know the b, so we can try to find the b. So we multiplied those two together, and I got 535.575 plus the b equals 59.7. And then we just need to solve for b. So we're going to go ahead and subtract 535.575 from each side. And so b equals negative 475.875. So there's the b. We got the slope, we got the b, we come up with a really good equation. We can call it a prediction equation because we actually can predict a little information, or predict a little of something that happens after this, which we could call linear extrapolation when it is outside of our data. So this is our equation. We just put the m and the b back in there. So let's go ahead and use that equation to actually predict a couple things. So let's say we want to know, hey, I wonder how long a baby would live, or what the life expectancy is if they were born in the year 2060. That's quite a bit beyond our data, but let's just kind of assume that the life expectancy will keep rising at that same rate. If medicine continues to improve, that it could happen maybe. So what we'll do is, since we're talking about the year 2060, we'll have to know, should we plug that in for the x or the y? And because our years were the x, then we'll go ahead and plug that in for the x. So we're going to say y equals 0.2775. We're going to plug in 2060 for the x, and then we're going to solve for y. So y will equal, do the math there, and it turns out to be 95.775 years. Okay? So approximately 95, 96 years is how long someone is expected to live and if they were born in that year. Now let's do the reverse. Maybe we want to know, hey, I wonder what year somebody would be born if they were to live to be 150. Will that ever happen, anytime soon? So what we would do there is we would actually plug that in for the y. So we'd plug in 150, and we would solve for x, 0.2775x, and then minus 475.875. So you get that? So we would solve for x, and that would be by isolating it. So we need to add that 475. So we add the 475.875 to each side. And I'm sure I'm going to run out of room here. So I've got 0.2775x, and I go ahead and add those two together, and I got 625.875, and I have one more thing that I need to do, and that's divide both sides by the 0.2775. So I divide both sides by that, and I'll just write that last step, which will actually be the answer on the next one. Okay? So I would say that x equals, when I do that division, it would be 2255.4. So we would say maybe by the year 2255. And that's, again, assuming that they keep increasing their life expectancy every single year by that same rate. Okay? So that should help with 5-7.